Hello guys, my name is Sandip and today we are going to start the second session of your fourth chapter, right? Okay. In the previous session, if you do remember, we have learned what are the different forces. What is force actually? It is nothing but pull and push, we can say, right? We have taken that example, if you do remember specifically, that car is, you are pushing the car, your brother and you are pushing the car. Then also pull is also the force, right? We also have studied a lot of different types of the forces, that is gravitational force, then we have the nuclear force. What are the other forces? I told you there are total four forces, right? First one is gravitational, second one is, let's say, electromagnetic force, third one is strong nuclear force, fourth one is weak nuclear force, right? So we can say there are four different types of forces, right? We have seen these things. Then we also segregated the forces according to contact forces, non-contact forces. If you do remember, we talked about tension, normal, friction, etc. Then non-contact forces like gravitational force, electrostatic force, those are our non-contact, right? Then we also talked about the equilibrium, then first law of Newton's laws of motion. So I hope that everybody now remembers all those things. So now we are going to move our second section of this force and pressure chapter. Okay, sure. So let's start. So first of all, let's see what we are going to study. Right, as I said, Newton is going to be there with us for up to 11th and 12th, right? So this scientist is really important for us. And so today what we are going to study: normal reaction, tension, free body diagram. If you do remember, we already talked a lot about the normal and tension. You also know, right? Today we are going to solve some questions. So we are going to study in detail what are the normal forces, what are the tension. And the free body diagram also explained about something about this one, right? Free body diagram means draw how many forces are acting on that object or body. This is called as free body diagram. Okay. Then now when we say normal reaction or normal force, do anybody remember what is normal force? I drawn the diagram something like this. If you do remember, and I call this as the normal force. Okay. So let's see what's normal force. Now consider a very simple example. Consider you're standing on a ground. Now you are standing on a ground. Tell me which force is acting on you. We already know that Earth's gravitational field is attracting you, right? That's very good, right? So Earth is acting force on you. Earth is attracting, we can say. So Earth's attraction is towards the center. Then tell me one thing. Who is stopping you to go toward the center of the Earth? Who is stopping you? Floor? Can I say floor? That's right. Floor is stopping us from going towards the center of the Earth. Then, now think on that. Earth and floor, right? Earth and floor, do they have any comparison with their forces? Can floor stop you from going towards the Earth? No. Then how we are saying that floor is stopping the Earth from attracting you toward the center, right? So remember what we can see here. Consider if you are standing on the ground like this. Okay. Now, whatever is the force which Earth is attracting, with which Earth is attracting you, we call this as mg force. Right. Now consider, let's assume your mass is, let's say, 50 kg. Yes, let's take 50 kg mass. Acceleration due to gravity is 9.8. That's good. So if I do this calculations, I'll get something like this: 490 Newton is force. Right? So Earth is attracting you only with this amount of force. It completely depends on only this G part and whatever is the mass. Right? So as your mass is very less, 490 is not that big a force. So obviously Earth can provide that much of opposite force which it is providing, like this, on you. Therefore, we can say those are equal and opposite force. Though Earth can provide lot of force, right, which depends on obviously the mass of the body. If you consider a very big object, right, plane or aeroplane, we can say, right? That mass will be very high, right? So what we can say, Earth will attract it with that much of force, but still the ground on which it is standing can apply the opposite force, which is going to equalize those two forces, right? So this ground or floor, we are going to call this as a normal. Very simple concept, right? And we also know that normal. What it is doing, it is actually providing the neutralizing force, we can say, right? Which obviously will stop you to go towards the earth. Okay, so we can say this is our normal force now. Now let's talk more about this normal force. So this is our basic diagram, right? On any table, consider any block is kept like this. Just okay. As we already know, Earth is doing what? Attracting that block towards where? Towards its center. Who is stopping it? The table is stopping in this case, table is stopping it, right? So table is applying the force N, which should be equal to how much? Which should be equal to mg. Mg is what? Mg is the force applied by the earth on the object, or we can say this is nothing but the weight of the object, right? So there are two forces acting on that block, that is mg and normal. Normal is applied by table, mg is applied by earth. Simple. Now consider if I put a very bigger heavy object here. Consider capital mg, right, on this table. What will happen? Table is also going to apply the same force, we know that, right? En, let's call this as n1, let's call this as n2, right? So table is applying the normal force to both the objects, right? Now what happens if this force is very, very high? This mass is very, very high. What will happen? Simple, table will go down, right? So there is obviously a limit for how much force, how much normal force, we can say, this table can apply on that block, right? If this mg, total mg, whatever is the mg, is exceeds that normal force, obviously it is not going to be in equilibrium. We have talked about the equilibrium, right? If one of the force is greater, this whole object will come down, and obviously in this case table will break, right? Okay, so now, so this is our normal force. Now one more concept, very important, you are supposed to remember about this normal force is, first of all, it's a contact force. I can say it's a contact force, right? We know that, we have already seen this in the previous session. Then remember, this is the type of electromagnetic force. So I can say this is electromagnetic force. Simple. Then what else you should remember? The very, very important concept which we are going to use throughout the 12th and your entrance exams. That, remember, third point is very important. This force acts perpendicular. This force acts perpendicular to the surface. Now let's see what is the meaning of this. So these are the 3 points which are very, very important for us, right? So third point, as I was saying, very important point. This force acts perpendicular to the surface means what? Let's see. Now for this table, we can consider this table, right? Let's forget about the second block, concentrate on the first block only. I know there are mg forces there, and table is applying the force which is equal to normal force, right? We also call it normal. Why normal? Normal means perpendicular. So in this third point, you can see why we are calling this force as a normal point or a normal force, right? So what I was saying, the table was applying the force perpendicular to the surface. Surface means what in this case? Obviously table. So if you can see, this is the surface, and tell me how much is this angle, right? This angle obviously should be, I can say it is 90 degree, right? So let's say this is 90 degree. So normal force always acts perpendicular to surface. mg, we also have studied about the mg. mg means what? Gravitational force. Gravitational force, remember, always acts downward, right? Okay, now let's take one simple example on this. Now consider this is the inclined plane. We can see the inclined planes, right? Okay, we can say this is slide, right? Slides for children on the garden, right? So those slides are inclined plane. Now consider if any child is on that, or just consider now a block is kept there, right? Let's see how many forces are acting on this. mg, remember, mg should always look like this, that is downward mg. Okay, and our normal, again, normal is perpendicular to the surface. So who is our surface now? This is our surface. So let's draw one force perpendicular to this one. Perpendicular means this angle should be 90 degree, right? We know this point. So now you can see here, normal is not necessarily always upward. On horizontal table, we can see normal is acting upward, exactly upward, right? Here you can see normal is inclined to the slide through 90 degree, right? Simple. Then consider one more case. Now this is the wall, right? We have our walls in our rooms also, right? This is our horizontal wall. This is which can call this is our floor, right? So floor is horizontal, wall is vertical. Now consider if I'm keeping one object like this, right? First of all, tell me whether this object will remain there. If you just keep one object like on the wall, right? Will it stay there? Obviously not, right? Why it is not staying there? Because we know mg is acting downward. So this mg force means this Earth's gravitational attraction is going to bring that object downward up to which level? Up to ground, we can say, right? Now consider I am holding this object like this. I'm holding like this object with my palm. What will happen? Obviously, it will stay there now, right? So, what we can say, I am applying some external force. I'm applying some external force. And what about normal in this case, right? Now, just let's not worry about this applied force. We will assume that applied force is there, and let's talk about the normal. Now normal, as said, again very important, normal is perpendicular to the surface. So what I'm supposed to do, draw one diagram which is perpendicular to this, right? And let's call this force as normal. You can see again the surface and this angle is 90 degree, right? So this is our condition that the normal should be perpendicular, that is 90 degree to the surface. Okay, so what we have learned about the normal, first of all, 3 points are very important. First, it is a contact force, right? Means obviously there should be contact between two objects, and then it is electromagnetic force. And the most important thing is this force acts perpendicular to the surface. Now, give me one example, one answer, quick answer to this question. Consider this is table, and one block is kept on the table like this, right? We already know now that force is acting upward and mg is acting downward. We already learned about the equilibrium. This is 90 degree, right? Is any other forces acting on that? Yes, anybody can guess, right? So I can say only two forces are acting on that. There is no other force there, right? Now, tell me whether this block is in equilibrium or not. Simple. We can say mg, as long as mg and n are equal, then we can say that body is in equilibrium, right? We can again consider our example of laptop in front of you or mobile in front of you, right? It is at equilibrium, right? It is at rest, right? Now, what I'm going to do, I'm going to pull this block upward with external force, right? Now let's see what happens. right? This diagram will become something like this. If this is stable, and now as I'm pulling this, right, and let's just, we can carry our laptop or mobile, right? What will happen? There is no contact between table and our laptop or this block. In this case, we can say, tell me, is there a normal force in this? First force is mg, that is right. Is there a normal force? No, obviously not. There is no contact between the table and the block. Obviously, there will be no normal. So who is pulling this upward? Obviously, external force. We have already applied the external force. So now F and mg will balance each other. Then we can say that obviously it is in equilibrium. As long as you keep pulling that laptop upward or pulling that block upward, we can say, right? So this is the normal reaction and external force mg. These are the different diagrams we can see, right? Now let's move out to our next point. So here you can also see table, block is kept on the table. Weight means mg. I can say this is nothing but mg, right? And normally it's acting upward. Who is giving the normal force? That is surface. In this case, table, we can say, right? Now, why this normal force exists there? Or we can say, why exactly is the normal reaction is there, right? Because the normal force is a electrostatic force, right? So whenever there is a contact between these two objects, box and table, we can say there is a electrostatic force of repulsion. We can say electrons will come together and they will repel each other. Therefore, we can say there will be a normal force. Yes, one more important point we should write. Also, you can write this in our previous question, previous points here. This normal force is always pushing. And I add one more point here. This normal force is a pushing force. Pushing force means what? It is always pushing the object. Here you can see the on the table is actually pushing that object, right? Here on the slide, it is pushing the object everywhere. Normal force, you can see it is only the pushing force. Okay. Now, yes. Now here you can see, we can see one question here. There is table and block. Two blocks are there, right? One block is kept on another, right? And we want to calculate the forces N1 and N2. What is they are saying? N1 is the force between these two blocks, right? Red blocks and blue blocks, we can say. And N2 is the force between surface and our M2 box. And we want to calculate this N1 and N2. Let's say how to calculate that, right? Now, if you consider this table, surface is our table, and we want to calculate N2. N2 is what? How much force the block is applying on the table, or by how much force Earth's gravitational field is attracting those two blocks. This is nothing but our uh, weight, we can say, right? So first of all, let's mark how many weights are there. So tell me, for this block M2G, can I write M2G is weight or W2, right? Similarly, for this block M1G, it is also acting because what we can say obviously here, M1G is also acting downward, right? Okay. Similarly, for N1, let's talk about the N1 first. Now, N1 is the contact force between two blocks. First block is red one. Let's draw the red block here. And then we have this blue block. Let's worry about only these two forces, right? Now let's see. Now for the red block, what I can say, this blue block is what? Surface, right? So how much force it will give you, apply on that red block, right? Obviously 90 degree I can say. So this angle will be 90 degree. That's right. They have called this as N1. So let's write this as N1. And who is another force which is acting on that red block? Obviously Earth. Earth is what? Earth is also attracting it with, let's say W1, or I can say M1G, right? M1 is mass 1 and M2 we can say mass 2. Okay. So what you can say? Just equate these two forces. We know those that block is in the equilibrium. So I can simply say N1 is equal to what? W1 or M1G, you can say. So this is my basic formula, right? Now let's talk about the M2. So now let's consider only M2. Now for M2, can I say this block is acting as the surface? Small block? Yes, obviously, right? So even though it is upward, it is also going to apply the force which is same, that is N1. When we say N1 is the force applied by M2 on the M1, we also know that M1 is also going to apply the same force on M2, right? This is Newton's which law? Third law. Every action has equal and opposite reaction. So if M2 is applying some force on M1, M1 is also going to apply same force. So how much force M2 is applying on M1? That is N1, right? So can I say this N1 is acted on this block? That's right. Which block? Blue block. Blue block, we can say. And what about the other force? Can I say that is W2 M2G? We are only talking about which one? This blue box only, right? And let's draw surface is also there, no? So let's not forget the surface. Surface means we can say table is also there. Now this table is also going to apply the force on that blue box, right? That force is equal to how much? Can I say it is N2? That's right. It is equal to N2. Now let's equate these all forces, right? What I can say, vertically upward forces, similar. Here also we have done the same thing, but now here are three forces. So I'll write here, vertically upward forces is equal to downward forces. Let's write this upward force is how much? N2. Downward forces, N1 is also downward plus M2G. That's right. What about N1? How much is N1? We already got the N1's value in the previous block. So this will be M1G plus M2G. So this will be our formula for N2. So we got the N1 as well as N2 in these two cases. Okay. So this could be the question. You should be able to solve this type of questions. Right. Now let's consider how many find the normal reactions at all four interfaces. Interface means where two objects or contact are in contact, we can say. So consider M1 and M2. Where is the contact? Here is the contact. M2 and M1. Here is the contact. What we can say, M2, this M2 and there are two M2s. Both are pushing the M1 upward. Similarly, F1 is also pushing them downward. Right? What about the surface? Surface is pushing M2s upward. Right? So these are the normal force. Let's call this as N1, N2, N3, N4. Right? Now, simply what we are going to do, just draw one FBD. FBD means what? Free body diagram. Free body diagram means what? To draw all the forces acting on that, right? So let's talk the block by block, right? So first one, let's talk about this M2. There is another block M2, right? So there are two M2 blocks. Let's draw the free body diagram on that. That is MG. Can I say M2G is acting downward? Yes. Here it is also M2G is also acting downward. We have shown the N1. N1 is applied by whom? Table, we can say, or the surface, which is acting upward in this case. Here I can see N2 is acting upward. Then M1. M1 is also giving some force on to this M2, we can say, right? So can I say this is M1G? M1G also applying the same force on this one, right? So this is M1G and M1G. Two forces are acting on these two blocks, we can say, right? Okay. So let's draw the free body diagram of the M3 block. Right? Instead of M1G and M2G, let's write this as N3 and N2. How I can write the N3 and N2? Now let's focus on this small part. What I said, M2 is pushing the M1 with the force N4. Similarly, can I say this M1 is also pushing with N4, pushing the block N2 downward with N4. Also here I can write N3, right? So let's write here, this is our N4, this is our N3, right? Now Let's talk about the block, the bigger block. For bigger block, how many forces are there? Obviously, gravitational force is there. Though it is not in the contact with the surface, gravitational force, we already know it is the non-contact force, right? So I can say M1G is there. Then N4 is acting upward. N3 is acting upward, right? Okay. So I got this type of forces. Now let's equate the forces. We know upward forces should be equal to downward forces. So what I can see here, N3 plus N4 is equal to M1G. I will get this relation. Now let's talk about this block. What I can say here, upward is N1 is upward, N4 is downward, plus M2G I can say. For this diagram, what I can say, N2 is equal to what? N3 plus M2G, right? So this is how we can calculate, right? If you want to calculate this one again, what you can do, you can just add these two, N1 plus N2. Here you will add N2 plus N3 plus N4, we can say, right? Let's try to add this two. Can I say N1 plus N2 is equal to N3 plus N4 plus M1G plus M2G. Sorry, these two both are M2G now. So let's write this as M2G. Or what is N3 N4? That is nothing but M1G. 2 M2G I will get like this. Okay. Also, you can see the symmetry here. M2 and M2 both blocks are what? Equal masses. They have the equal masses. So what I can say? The forces which surface will act on them, aren't they equal? So can I say N1 is equal to N2? That's right. Let's call, yeah. So N1 is equal to N2. So I can say this is nothing but 2 N1 is equal to M1G plus twice M2G. From this I can get N1. N1 is equal to what? M1G plus twice M2G divided by 2. I can also say this is nothing but N2 because we already know N1 and N2 are same. Similarly, you can see the symmetry between what? N3 and N4. They are also similar. So can I say 2N3 is equal to? I can also say this is nothing but 2N3 is equal to M1G, or N3 is nothing but M1G by 2, and this is also our N4. Right? So this is how you can solve the equations using the normal forces. Okay, good. Now let's move to our next force, that is tension, right? So tension, whenever there is a tension, I'm not talking about the tension of the studies, right? Tension of the force, tension as a force, right? Okay. So tell me, we already seen in this previous session also. Tell me, when we say tension, which game do appear in our mind? That's right, tug of war, right? So let's do one thing. Here I can see two cars are there, right? Normally we know that tug of war, children's play tug of war. It's also the game, right? So now let's see who wins in these two cars. Let's watch this small video.
Control off.
Ready in 3, 2, 1, go.
Come on! Come on!
Right, so one car we can see is of Ford Ranger, and second one is of Toyota.
As you can see, there's not a lot of movement going on. The Hilux and Ranger are just spinning their tyres and going absolutely nowhere. Time to up the ante. Now here, the cars are set to low-range four-wheel drive and have their rear differentials locked. Again, there's plenty of action underneath the cars, but not a lot of movement. We did this a few times and even switched ends and found that if one driver got the jump over the other, we had a result. The Hilux won one round and the Ranger won another. It was plenty of fun, but not a real result. Worth noting too that the Ranger is 200 kilograms heavier than the Hilux, which should have given it a bit of an advantage. As in part of our testing, we hooked up our production team's Everest, which...
So this is the tug of war we can say between the cars, right? You say no result is there because both won the game once and once. Okay. So what we are going to talk about is this tension in the string is the one important force. right? So what we know about the tension, let's write the points of that first, right? So first points I can say, tension, is it a contact force or non-contact? Contact force, right? We have seen this in the previous session. This is the contact force. Then what else we can talk about? This is again the electromagnetic force or electrostatic force, we can say. This is also the electromagnetic force. And one important thing about this tension is, we are going to say this is the pulling force. Remember, this is the pulling force, man. So what is the meaning of that? I also explained this in the previous session also, right? If you tied one block here, tension will be applied upward. Similarly, consider if you connect another block here, second block, what will happen in this case? You can see for this block, or let's say A block, and this is our B block. For A block, this string is pulling it downward, and same string is pulling B upward. Why? Because we already know that it is the pulling force, right? Simple. So this is the tension we can say. Now let's consider one example on this. Consider there is a water, and you have the bucket and string like this, right? So bucket is connected here, so you fill the water bucket with this water, and now you want to, we can say, you want to pull it upward, obviously, right? String is there, means tension will be there. Tension is always pulling force, right? So you're pulling this water. Now consider one more example. Obviously this is going to be very difficult for you, so you must have seen something like this, which is called as pulley, right? And now what you are going to do, all this like this. Yeah, so this is called as pulley. So instead of directly pulling this water bucket, we can say you attached pulley here, and now you're pulling this bucket, right? Tell me which case or which problem or which method going to be easy for you, first one or second one? Obviously second one, right? Why? Because we have used some pulley there. Pulley means what that pulley is doing. Pulley is actually helping us to pull this water, right? So again we can say there is a tension in this bucket and string, and as we are pulling that string, we can say this will possibly, or we can say this will reduce the effort of the person, right? Therefore normally we use the pulley in many applications. So pulleys are very important application, we can say. Okay, so this is tension, we can say. Let's see what else we have, right? So in here we can say tension, string is attached, so tension is in the string. Then obviously mg, we can say. In the previous case when there was a object kept on the table, what we say, tension is equal to what? Tension is equal to mg, right? Sorry, normal is equal to mg in the previous case, right? Here what we are going to say, tension in the string, so we can say tension is equal to mg, we can say. So tension is also electrostatic. Electrostatic is again the type of electromagnetic force, and we know it is our pulling force, right? Now let's say this question. Question says there are two blocks, right? I also drawn this type of diagram, and we want to find the tension in the two strings. This represents the ceiling, so this tension, this string is connected to ceiling, we can say, right? So let's draw one tension here. What I said, this is our tension here, and this is also our tension, right? Also let's mark another forces. What are the other forces acting on this? There I can say this is capital mg, that is weight, right? And here it is small mg. Okay, so these are the forces acting on all the system, we can say. Okay, so now we want to find the tension in the two strings. So this is our first string. Let's call this as tension as T1. Here, this is T2. Should I say this is T3? No. Remember, one more point. Let's add one more point to our concept note of the tension. For massless and inextensible. Remember, in questions, they mostly are going to say that the string is massless and inextensible. First of all, massless means what? The mass of the string is very, very negligible. We are going to consider with respect to block. And inextensible means what? It is not going to extend, right? Its length will not change, even though there is a force applied on that. Right? So what we are going to say, for massless and inextensible string, tension is same at every point. Let's add this another point here. Okay, what is the meaning of that? In this our diagram, what I'm going to say, as long as the second string is same, I'm going to say this tension is T2 only. There is no change in that. Okay, now what we have to do, we have to find out the tensions in these two strings. So first of all, we want to find the T2 and T1, both the things we have to find out, right? So what we need for that, first of all, let's try to draw the free body diagram. Free body diagram means what? Mark all the forces on that diagram. Let's talk about this capital M block, bigger block. So if this is my capital M2, let's say, let's mark how many forces are there. First of all, I can see mg acting downward. Can I say this is capital M? No? So instead of M2, let me say this is capital M. So this force will be capital M into G. Which one is the another force? T2. Is there a normal force there? No. Why? Because it is not in contact with any surface. So no normal force. Simple. Right. So there are only two forces I can say. Is that block is in equilibrium? Obviously it is in equilibrium. So can I say upward forces is equal to downward forces? Obviously. So let's say T2 is equal to mg. I got my first answer, that is the tension in the second string. Now let's talk about the upper block, small block, right? So small block have the mass small m. So what I can see, this is our small mg. Then which one is the other force? Yes, I can see the T1 there. That's good. One more force is acting on that small block. Yes, you can see T2 is also acting there, right? So I also have to consider the T2 in solving the equations. Let's solve the equations again. What I can do, upward forces is equal to downward forces. Tell me the equation now. Yes, that is T1 is equal to, this is small mg. Okay, let's me write this as a capital mg, right? This one is our capital block. So this is our small m into G, plus T2 is also there, right? So we also have to consider that T2 part. Now I can also substitute the value of T2 from the previous equation, that is mg plus capital mg. Can I say this is small m plus capital M into G? Right, so I got the two answers, one for T1, one for T2, right? Or simply what you can see, what we got T1? T1 is the addition of both the masses into G, right? So T1 is equal to m into T1, right? T2 similarly, T2 is only, T2 means which we can say this tension, right? So T2 is only pulling the capital M block, we can say, bigger block, we can say, right? Therefore, its answer is only mg. T1, you can see T1 is also pulling this small m and also pulling the capital M. So we got the answer as addition of both the masses into G, right? So I'll give you one example here. Try to tell me the answer. What will be the answer here? Okay. So consider this is the block of, let's say, 2 kg, and I'm attaching another block here. let's say 3 kg, right? Now let's calculate. This is T1 and let's say this is T2. Yes, anybody. You can consider the G. Let's take the G. We already know G is equal to 9.8 meter per second square, right? But remember, in MCQs, when we are going to solve the MCQs multiple choice question for the entrance exams, we approximately going to consider this as 10 meter per second because it is easy for calculations, right? Okay. So tell me what should be the answer for T1 and T2, right? What I said, T2 is pulling, not pushing. T2 is pulling which block? Only this block. Is it pulling second block upward? No, obviously it is pulling downward, but the string is connected upward, right? So only we can see here T2 is pulling 3 block, right? So what should be my answer? M, capital M, I can say capital M into G. Can I say this is 3 into 10 or 30? That's good. What about T1? T1 is pulling both the blocks, I can say. So that will be 2 plus 3 into 10. How much? 50. What is the unit of force? Tension is our type of force, right? So unit is equal, we can say unit is Newton, right? Simple. Now, consider one more example. Now this example, it's important for your entrance exams, right? Which you are going to appear in 11th and 12th, right? So this concept, we are going to learn new concept, or let's say JEE or NEET. Okay. So now consider there is pulley. Now everybody knows pulley, right? We also seen one problem. Pulley means what? Along which there is a rope or string connected like this, right? Now consider on this string there are 2 blocks. One block, let's say 5 kg, and this block is, let's say, 3 kg. Okay, what I'm saying, there is a pulley on which the rope is connected, obviously, and this rope is connected to 2 blocks there, M, that is 5 kg block, and 3 kg block, right? So now what we are going to do, we are going to find out the forces, how many forces are acting on those, right? Let's see. So as you can see, let's talk about this 5 kg block. First force is downward. How much is it? Let's say M1G. Okay, let's do one thing. Let's call this as M1. Let's call this as M2. Okay, so first force will be M1G and second force will be upward. This is tension. Let's talk about this one. This will be my M2G and this is T2. Can I say this is T1 and T2? Yes. So everybody think on that. Is that T1 and T2? I'm going to say that this string is inextensible and massless, right? We have added one important point in our theory part, that tension in the string, as long as only one string is there, tension in the strings are going to be same. Those are not different. So I'm not going to say T1 and T2. Let's call them as T1 and only T and T. Right. So now tell me one thing. Think on this again. Oh, M1 is 5 kg, let's say. M2 is given as, let's say, 3 kg. Tell me one very important thing. Is this two blocks, right? So there is a system of 2 blocks or 2 objects, we can say. So are those 2 blocks or this system is in equilibrium or not? This is my question, right? Are those in equilibrium or not? If you do need the information about the pulley, we know that the string can rotate along the pulley, right? So these blocks can move upward, downward in whatever directions, right? Obviously dependent on their masses. So again, I will repeat question. Tell me, is the system is in equilibrium, that is at rest or not? Right? Right. What we can see here, let's draw the MBD for M1 separately. Right? So what I can say M1, I'll substitute the value, that is 5 kg. So my formula is what? M1G, no? So this will be, let's say, 5 into G, or let's call this as 50. 5 into 10, right? G approximately we are going to consider G is equal to how much? 10. meter per second squared. So let's say this is becomes 5 into 10 is equal to 50 Newton. It is anyway, it is a force, mg is a force, so it is 50 Newton. This is our tension. Then let's talk about the second diagram. This is 3 kg. M2G. M2 is how much? 3. 3 into how much? 10. 3 into 30. Oh, that will be 30, right? And tension is upward. Do you think anything is wrong in this one? Can you try and equate the vertical and vertically upward components and vertically downward components here? Yes. So here you can see T is equal to how much? 50. Here what you can see T is equal to 30. But as I said, tension in the same string is not going to change. So tension value of the tension, that is the force of that tension, should be same. Here we are getting 50, here we are getting 30. Is it right? Obviously not. Right? So what is the difference? What we can say in this case, this system is not in equilibrium. Why? Because forces are different. This system is not in equilibrium, I can say. Okay, so what will happen? Obviously, this 5 kg block, this is my 5 kg block and this is my 3 kg block. As it is not in equilibrium, it is going to move, right? If it is going to move, which one will move downward or upward? Terming the block which have the high mass or higher weight is going to move downward. Very simple thing. So who has the higher mass? This 50 Newton. This is 30 Newton, right? So obviously this block is going to move downward. How to show this by equations, right? We have obviously we have seen here that T is getting 50 and T is getting 30 here, which is wrong. I know that, right? So what we are going to do here, we are going to say there is one acceleration. If the bigger block, obviously of 5 kg mass is moving downward, it is moving with some acceleration A, right? Similarly, where the block, that 3 kg block is moving, it is moving upward. So let's show mass A upward. Okay. So what we can see in this case now, as this diagram, we need here mass acceleration A here, and acceleration for this guy is upward. Okay. Now let's try to equate the equation or solutions of forces. We can say here what we are going to say, if the acceleration is downward, this is not the force, we can say this is our acceleration. So what are the forces acting? M1G and T. If the M1G is downward and the mass is moving downward, tell me which one should be greater in this case, T or M1G? Obviously M1G needs to be greater than whom? Capital T. Is equal to what, right? Minus, I'm saying it is minus because M1G is greater. Is equal to what? Acceleration. We can say this is the resultant acceleration, right? Now, this is force, this is force. If we subtract force from force, we cannot get acceleration. So what I have to do? I have to substitute the mass also there. And we know mass into acceleration is force. So this is my new equations now, right? This is not in equilibrium. So I'm getting this equation, right? Similarly, anybody can guess what should be the equation for the second object? Again, acceleration. 3 kg is also moving with the same acceleration. Remember, acceleration is also going to be same for both the guys, both the blocks, we can say. So if that block is moving upward, which force should be greater, T or M2G? That's very good. T should be greater than whom? M2G. What I should get? Is it A? No, I should attach it mass. Whose mass? M1 or M2? M2. So I got the two equations there, right? Simple equations I got there. Now what I am supposed to do? Just let's solve this two equations. How to solve these equations? I already got the value of M1G. Let's substitute in the first equation, right? So I'll write this is 50 minus T. What is M1? 5, you know. Let's write 5 here. This is my first equation. This is my second equation. Let's write M2G is how much? 30 we got. This is how much? 3A. This is second equation. Let's add these two equations. What will happen when we add the two equations? We have to add LHS side to LHS, RHS side to RHS. So what happens if I add RHS to RHS? I will get 8A here. What about this one? T and T are going to get cancelled, right? Minus T plus T will get cancelled. 50 minus 30 is how much? Let's say 20. So from here, I'm going to get the answer for A, that is 20 by 8. Or can I say 10 by 4? That's right. Can I say 5 by 2? That's right. So I got acceleration. What is the unit of acceleration? Anybody know? That's right, meter per second square. So I got the acceleration. So with this acceleration, these blocks are going to move, right? The bigger block going to move downward and the smaller block is going to move upward. Now we got the acceleration. Now they will ask how much is the tension in this strings. So they will either ask what is the acceleration, and the second thing they could ask is what will be the tension. So we got acceleration here. Let's substitute this equation into our normal formula. What I can say here, acceleration in any formula you can substitute. Let's substitute the value of acceleration in the first equation. What I will get, 50 minus t is equal to 5 into acceleration is how much? We got the value, that is 5 by 2, right? So can I say this is 25 by 2? That's right. I want tension, so let's take tension to the RHS side. It is negative here, it will become positive. What about this 25 by 2? Let's take it to the LHS, so it will become like this. Right, now we know how to solve this one, right? Very easy. By 2 is equal to tension, or let me write the tension on this side. 100 minus 2, 25, 75. 75 by 2 will be my answer. What should be the unit? Newton. We know the forces unit is Newton, right? Okay, so this is how we can solve the questions, right, of the tensions. Okay, so we already learned about the normal, we all learned about the tensions, right? We already know what are the important points we should remember in normal and tension, and also we have seen some examples how to solve the examples for normal and tension, right? Now next point is our free body diagram. So free body diagram is nothing, we have already seen the forces, we have already written all the forces of the objects. That is nothing but free body diagram, very easy to understand, right? So this concept is not new for us now. We know how to resolve the components, or we can say forces, right? So one more thing here is the resolution of forces. We are going to study this one now. Resolution of forces means what? Let's talk about this a little bit. So consider there is one force which is acting like this, right? What we are going to do, we are going to draw two axes. We know this is called as x-axis. Let's call this as y-axis. So what I'm going to do, if this angle is theta, right? Let's say this angle is theta. I'm going to get two forces which are going to give me the same result of the same force, right? Now simple, consider, let's take one example. If the object is here, right, and if you apply the string like this, right, with let's say 10 Newton force, right? Let's consider this example first, 10 Newton force. Okay, obviously this block is going to move in the horizontal direction. Now consider the second case. If you apply the force in the, let's say, upward direction, what will happen? That block will go in the upward direction, right? So what happens if you apply the force like this? What will happen? It is going in this direction. Obviously we know the motion of the object in the direction of the force. So you apply the force here like this, the block is going to go like this, in this direction. Simple. Okay, now what I can say, if I apply the two forces on this same block, one force is here horizontal and one force is here, let's say 10 Newton and 10 Newton, where this block will go? That's important thing, right? Whether it will go horizontally or whether it will go vertically, right? You can try doing one thing at your home. Consider you have one table, right? Push the table on one side, right? Ask your brother to push the table from the perpendicular side like this, right? You are pushing like this, where it will go? Don't you think it will go into the, we can say 45-degree angle or little bit of incline, right? So I can say again this table will go like this only. So with the two forces, horizontal and vertical, we can say that block is going to move into the not horizontal, not vertical, but inclined direction, we can say. Or what I can say, this is my main force and these two are components of force. So let me call these two as components of our main force. So either you can apply the two forces in opposite direction, or you can directly apply only one force in our inclined direction. You are going to get same result, right? Now same thing we are going to talk about here. So when we say there is a force, right, what we can see, instead of this force, resolution means what? We want the two forces instead of the single force, which will be along x and y axis, means vertical and we can say horizontal direction, which will give me a motion in the same direction, right? So we already know how to draw these two forces. We have already seen this diagram. One will be vertical, one will be horizontal. Can I say one will be along the x-axis and one will be along the y-axis? Simple, right? So let's draw this one. So what I can do, I'll draw one small perpendicular here, and now this will become my one component. Let's draw another component here. Let's call this as second component. Okay. So what I can say, this component is called as EFX. In this component, we are going to call this as EFY. So this becomes my, remember, now let's do one thing. Consider I name this as, let's say O. O is origin. Let's call this as A. Let's call this as B. Right? So if we consider by geometry in triangle OAF, what I can say in triangle OAF, cos theta. Cos theta is equal to how much? Right? Adjacent upon hypotenuse, that's right. So adjacent is OA and hypotenuse is OF. How much is my OA? I named that as FX. OF is nothing but my F, force, right? OF is the name and F is the force. So using this formula, I can get the relation Fx is equal to F cos theta. So let's write here Fx is equal to F cos theta. Similarly, now consider sine theta in this case. Same triangle. What I can say, sine theta is equal to what? Opposite upon hypotenuse. Opposite is which one? AF. Hypotenuse is what? OF. Now here what I can say, OB, AF is nothing but equal to OB. Can I say that? That's right. So let's write this as OB upon OF. OB is what? OB is, I have written this as FY and OF is again F. So can I say FY is nothing but F sine theta? So let me call this as F sine theta. So very simple thing you should remember in this case, that there will be two components of our main component, which is making an angle theta with the horizontal. Which are those two components? One will be F cos theta, second will be F sin theta. Every time you can say this thing is true, right? But which one is F cos theta? Is vertical is F sin theta and horizontal is F cos theta? Is that like that? No. Remember, wherever there is a theta, the component which will be nearer to the theta will be F cos theta. Component which is further from the theta, you can see this OB component is away from theta, and this FX component is OA component is nearer to the theta. So component which is nearer to the theta, we are going to call that as F cos theta. Other one will be our F sin theta, right? So this is, remember this very simple concept. Okay. Now if you know this concept, we can draw free body diagram. We already know how to draw the free body diagrams. We already seen the free body diagrams in, let's say, here also we have seen the free body diagrams. We have equated these relations. Here you can see we have equated this relation, but it was not in equilibrium. We also know now what to do if it is not in equilibrium, right? There is one component of acceleration we should attach. Then here also we drawn the body diagram, free body diagrams, right? Vertically upward, vertically downward things, right? Right. Everywhere we have already drawn the free body diagrams. We have equated the upward component with the downward component. We can also equate the horizontal component with the horizontal component, which is going towards left, which is going towards right, right? And what happens if the component is not upward or downward? Here, we have already seen one component here, normal. When we are talking about the normal at the start of the lecture, normal we know that it is the perpendicular to the surface. It is not vertical. So I cannot say here that En is equal to mg, right? Because En is not vertical. This will be wrong. So what we have to do? We have to resolve that component. Resolution means what? We already learned about that, right? So we now know how to resolve the component. So now we don't have to worry whether the component is vertical or not. If it is inclined, still we can get the answers and we can resolve that component. Once you resolve the component, you are going to get one vertical component, one horizontal component, and then we can normally equate the vertical and horizontal components, right? Now, how to equate those? Let's see. Now we will take this diagram, right? This is the diagram, and let's see how to equate those components. Consider same inclined plane here. I'm drawing the same inclined plane. Draw this here. Let's say this is our angle theta, and one block is kept here. Now we already know if the block is there, mg is going to act downward. Remember, wherever is the object doesn't matter. Mg is always acting downward. What about the normal? Yes, normal is perpendicular to the surface. Can I draw it like this? That's very good. Now consider someone is pushing this with the force here. Okay. Now there are three forces. Now we want to draw the free body diagram, right? Let's see how we can draw the free body diagram in this case. We already know for the free body diagram what we need, the vertical, or we can say the horizontal components. Now only mg is vertical in this case. Normal is inclined. This force is also inclined. So we know the process now. We have to resolve these components. So let's see how to resolve this component. So let's talk about the force first, right? We have already seen here in our basic concept. Force we can find, we can draw two vectors like this, which will be, one will be horizontal, one will be vertical. Let's do the same thing here. You can see the force. Let's draw vertical and horizontal components. So this will be my horizontal component and this will be my vertical component, right? Good. Now, if you do remember, I said the component which is closer to the F, we can say, no, not F, the angle, so component which is closer to the angle is F cos theta, and which is away from the angle, it is F sin theta. Now, where is theta in this case? I cannot see the theta anywhere, but I can see the theta here. So, and you use some geometrical knowledge to find out which angle is theta in between these two. Think on that. Let's me call this as angle 1. Me call this as angle 1 and this is angle 2. Think on that and tell me which could be the theta. 1 is theta or 2 is theta. Right? So let's see if this is my theta angle. Right? Force is also parallel to this one, like this. So if I draw horizontal like this, can I say this is also my theta angle? Obviously, if these two lines are parallel, this force and this surface is parallel, so they are going to make the same angle here. So in this diagram, I can say first angle is my theta. So I got the theta. That is important thing. Once we got the theta, it is very easy. So this becomes theta, the component which is closer to the theta. This is horizontal component is my f cos theta. Here I can say F sin theta. Right. Once I resolve this component in this F into two parts, now we are not going to consider this force in our free body diagram, right? Because we have already substituted two forces for that single force. That two forces are going to provide same effect that of this capital F, right? So we are not going to consider this capital F now. We are going to consider F sin theta and F cos theta, right? Now let's talk about this En. En is also inclined. So what I am supposed to do? I will need the two forces there. Let's try to draw two forces for F sin En also, right? So first will be like this, and second will be like this, right? Again, I need the theta. So first angle is theta or second angle is theta. We have to see that. Let's use our geometry knowledge. So what I can see here in this diagram, this is my horizontal line like this. This is my theta. Object is placed. If I just remove object, this is my En, right? En is making 90-degree angle here with the surface we know. So what we have drawn two components like this. One is this, one is this. So tell me, this is my one, this is my second. Which one will be our angle theta? Right? So yes, here you can see these are alternate angles. So this will be my theta. Still I haven't got first is theta or second is theta. So if this angle is theta, this becomes my 90 minus theta. If this becomes 90 minus theta, this becomes my theta. Remember this part, right? So what I can say in this case, my second angle is theta. And once I got the theta, then it is very easy to calculate the component. The component which is closer to theta will be my En cos theta, which will be away will be my En sin theta, right? Good. Now again, we know once we got the two component, we don't have to consider this En in our FBD, right? Now we got all the components here. So let's equate. There are two types of component now, vertical components and horizontal components. So what we are going to do, let's make two columns here. First one is, let's say, horizontal. Second one is, let's say, vertical. Okay. So let's talk about the horizontal forces. Tell me which are the horizontal forces here. How many forces are there? This is mg is 1. Let's me number them. This is 1. This is second. This is third. We are not calculating now. We are not considering this EF, right? This En cos theta, let me write it bigger. That is En cos theta. Let's call this as 4. And let's call this En sin theta as 5th. So I got the 5 forces. Tell me which one are the horizontal. First is vertical, downward. Second is horizontal, yes. Third, fourth are vertical. Fifth is horizontal again. Now, tell me what we have to do. Going towards right, we have to equate those to the En sin theta, right? That is going towards left. We can say why we are equating, because now this is in equilibrium. And we know it is in equilibrium. We are going to equate those. So let's equate the horizontal forces. What I can say, F cos theta is going towards right, like this. Should be equal to what? Going towards left. Who is going towards left? Only 5th force. So I can say En sin theta. Let's talk about the vertical now. There are only two forces horizontal. Now vertically, there are mg. First force is there. Second is horizontal. Third and fourth are also vertical. So what I am supposed to do here? Equate upward forces to the downward forces. So let's see how many are the upward. I can see En cos theta and F sin theta. Right? So En cos theta plus F sin theta are upward forces, right? Equate those to what? Downward force. So I'll get these two equation using free body diagram. So you know now how to draw the free body diagram. If the vertical and horizontal forces are there, make two columns, equate those. If it is a inclined plane, we have to find the components. We have to resolve those two forces. We now also have seen how to resolve these two forces. And once we resolve also, remember this thing important. Once you resolve the original force, don't consider that force when we are using or preparing the equations. Okay, so this is about the free body diagram, we can say. Okay, now here I can see one more diagram is there. F, N and mg is acting downward. So we can consider this diagram as acting on the, let's say, block is kept on the table. Mg is acting downward. Force that we are pushing the block with force, and En is acting upward. Right? So there are only three forces. Very easy to say. Right? Can I say En is equal to mg? Yes, En is equal to mg. What about F? Is anybody equating F? No, horizontal force is not equating with any of the forces. So can I say this is in equilibrium? No. So I can say this is non-equilibrium diagram. So obviously if you apply the force here, what will happen? That block is going to move in this direction. So block will move up to this one. If I want to bring this in equilibrium, what I have to do? Right? What I will do in this case, I will apply one force like this, right? Let's call this force as F dash. And how much its magnitude should be? Whatever F is there, let's say this is 10 Newton. I should apply F dash is equal to 10 Newton from the other side. Now, can I say it is in equilibrium? Yes, right? So I can say F is equal to F dash, but original diagram was not in equilibrium. So we can say this is non-equilibrium diagram. Okay, so this is how we can find out the different types of forces also here. Okay, sure. So today we have studied about the tension, then normal, then we also have studied about the free body diagram, resolution of forces. It need not be only force, we can resolve anything, right? We can also resolve the velocity, whichever quantity is a vector, we can resolve those. To resolution, what is the important thing? In this diagram, you can see the component which is closer to the theta is our F cos theta. Component which is away from the theta is F sin theta, right? So there are many types of forces. We have already seen tension, normal, right? Then in next chapter, not in this chapter, in next chapter we are going to see very important force, which is also called as a frictional force. That is also one of the important force, you can say, right? And this chapter still has, we have completed the forces concept in this chapter. In next chapter, what we are going to do, we are going to see the concepts of the pressure, right? What is the relation between pressure and the forces? How to calculate the pressure on any object? Obviously, if you apply the force on any object, there will be pressure, right? So if this block, even on this block, you can see there will be a pressure. If you tied some object to the string, in case of tension we have seen, you can also say there is also a pressure. So what is the pressure and forces relation? Then what is the relation between what is the pressure of the liquid? You must have heard a lot of times, right? In case of dams, right, there is a lot of pressure built up on the dams or dams wall, we can say, because of water. So even water can apply some pressure, a lot of pressure, not some pressure, I can say. If the quantity is large, we can say water can also a big pressure, apply big pressure there, right? So we are going to study those into our next session. Okay, sure. So today we are going to stop here. If you have any doubts, please put your questions in forum, so I will accordingly answer them. Try to solve questions of this tension or normal or free body diagrams. Read the theoretical parts. That will be useful for your exam, right? And as I said, if you have any questions, just put those in your forum, right? Okay. So we'll stop here today. Thank you very much.